www.badass.com/become a member. All right, well, welcome everyone to BAD ASS HVAC, Near Perfect Comfort and Air Quality. This course is approved for 1 hour in continuing education units, GBCI, BPI, NonWholeHouse, among many others, and AIA, Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. Today, I will be your moderator. My name is Brett Little here at the nonprofit, the GreenHome Institute. And the question we're going to be asking today and learning more about is how can HVAC be made better and easily do it in a fashion that makes it more efficient and healthier for everyone. And real quick, a huge thanks to our top tier sponsors, Panasonic. Last year, they were big winners for the Green Builder Magazine Award for their one-way ceiling cassette. Mitsubishi provides heating, cooling, filtration needs all in one system. Today's low-load homes require right-sized equipment that most systems, especially gas-fired, cannot meet. Mitsubishi has low-load, high-efficient heat pumps that dehumidify and cool in the summer and work in reverse to heat in the winter. Going ductless reduces costs and makes it easier to meet the Energy Star 3 certifications and LEED for Home certification. Ductless mini splits can now be hidden in many different ways to meet your client's needs, and ducted systems can be used as well. Ducted systems are hidden behind the walls to ensure a beautiful space and can be retrofitted to replace a furnace in existing or single-family, multifamily projects. Hyperheat ensures an efficient heat delivery down to -13 degrees. Backup strip heaters can kick in during the rare but coldest of cold days. Each room of a house can be customized comfort while still being all electric and energy efficient for clients with different needs, and only heat and cool rooms as you need them. Multifamily and commercial centralized variable refrigerant flow or VRF systems work great on larger projects looking to serve whole buildings. These VRF heat recovery technology permits simultaneous heating and cooling. As this illustration depicts, a space can have many purposely designed areas, each area requiring a different heating cooling need during the day. Check them out over at MitsubishiComfort.com. And then thanks to our second tier sponsor, Ava Windows, aluminum recycled content windows and UPVC up to R7 in its thermal resistant. So check them out. All right, well, want to welcome back for a second time here, Nate Adams, who I've known for some time through various online forums, and always great to follow his work. He is the author of Home Comfort Book and has written or spoken for numerous outlets, including Healthy Indoors Magazine, the Journal of Light Construction, Green Building Advisor, Green Tech Media, Ohio State University, IAQ Radio, and the HVAC School podcast. He is super passionate about helping homeowners and HVAC contractors understand how homes really work and what the root causes of comfort and health problems are and how they can be addressed, not just the symptoms. The upgrades often result in electrification, where homes are converted to only using electricity, reducing air pollution both indoors and out. As co-founder of the HVAC 2.0 program, he helps HVAC contractors profitably solve complex comfort and health issues in their clients' homes with entry-level talent. So with that, Nate, I'm going to turn it over to you, and please do take it away.
Well, thank you, Brett. All right, can you see my screen?
Yes.
And hopefully just the slide. Okay, good to go?
Perfect.
All right. Okay, welcome everybody. And Brett, thanks again for having me back. This is kind of a fun topic. So it's kind of funny, the work that we've done. I started out as an installation contractor, and then we dug into the comprehensive building performance upgrade market, and we have created a process for doing that. But part of what we found is a lot of houses aren't that incredibly screwed up. So about half the time from the HVAC 2.0 contractors that we're working with, you can basically change the HVAC to the right piece and make a few changes, and you can solve all kinds of comfort and air quality problems just with that upgrade. But the problem is, and I mean, I don't mean to take a shot here, but typically the green building community is specifying kind of unusual stuff that not many people are familiar with. and it's not super easy to install. Like it's the first time for a lot of people, and so it can be tough to get contractors to do what you are hoping for them to do. So we have stepped back and thought, all right, what is a simple system that we can put together that 90% of contractors can do, that will work in 90% of homes, that will deliver very good comfort and air quality at least 90% of the time. And we've been tweaking this for a while, and then gave it the cheeky name, BAD ASS HVAC, mainly because our main audience for this is the HVAC industry, and it's pretty fun. We went to AHR, the big HVAC show, back in January, and I was talking to somebody at a booth, and a couple guys that had seen my presentation walk on through it. They're like, "Yeah, BAD ASS HVAC." And I'm like, "All right, this is going to stick." So this is meant to be sticky and cheeky. But at the same time, there's a lot of really good science behind this, and this is something that should work in most houses, and most contractors should be able to install well. The install on this doesn't have to be perfect to have it work quite well. So we're, again, trying to manage all those things. So we call it one system to manage it all. Initially, I used Lord of the Rings ring for this, but I figured somebody would not like that, so I don't. But thanks to Bob Krell of Healthy Indoors magazine for this photo. Okay. Now, if you want to read about us developing this stuff, this is the website for Energy Smart Home Performance. This is our practice, which we're starting to wind down, frankly, because it's largely done what we need it to do, which is help us develop the process for scaling this. Because particularly if you think about the electrification side, there are about 100 million existing homes. About 40 million are already electric, mainly in the Southeast. But if you want to electrify a whole bunch of houses by, say, 2050, that's 30 years, we need to be doing 2 million a year to get there. And so that needs a very different way of getting there. And that's part of what we did, figuring this stuff out. But there's lots of case studies here, so go take a look if you want to. This is energysmartohio.com, and then look at the case studies. Then a lot of the material you're going to see here, a lot of the charts and figures and so forth come out of this chapter of my book. So 4 of the 6 chapters of the Home Comfort book are free downloads. I wrote this mainly because there was no introduction to building science to bring somebody up to speed. So assuming you know nothing about building science and are reasonably intelligent, you can come up to speed with this book. And this is the second chapter, HVAC 101, and the HVAC 2.0 guys, it's almost all guys thus far, are sending this to clients, and it helps people understand, and you'll see too, what the different types of HVAC are, so that people understand that it's not all a commodity. It's not just a furnace, it's not just an air conditioner, it's not just a heat pump. There's different choices within that. So this is at NateTheHouseWhisperer.com. You can go download it for free. Okay, so let's dig in. What we're really trying to do is provide very healthy and comfortable homes. And when it comes to having a healthy home, you need good indoor air quality. In general, you're going to find agreement on these 4 buckets that we need to control. So we need to control moisture a whole bunch of different ways. You know, we need to control liquid moisture, which is water, and vapor, which is a gas form of moisture. We need to control dew point in the air and surface temperatures so that we reduce condensation. There's a lot of things there. Dust is really important because this very small particles, A, will get into our lungs, and B, if they're small enough, under about a micron, they will go straight through our lungs into our bloodstream. So kind of a freaky thing here. From diesel exhaust, there's a lot of heavy metals and ugly stuff in diesel exhaust, and it's extremely small. So every time you feel a whiff of diesel, you are breathing in heavy metals, and it's going straight to your blood. That's fact. So being able to control that's very important. That's also important, which we'll touch on a little bit about COVID. Chemicals is the third bucket you need to be able to control. So TVOCs, volatile organic compounds, carbon dioxide, ozone, radon, lots of things there. And then combustion is the last bucket. So if you're burning something, there's always something bad coming out of that, and you don't want that to get in the house. You don't want to breathe that. And really, ideally, we don't put it into the environment in the first place. So how do we manage those 4 buckets? You will be seeing this slide again and again. We manage it with what we call the 6 functions of HVAC. And this is in the conclusion of HVAC 101. And then HVAC 101 tells the story a little bit different way than what I'm doing here, but it's the same things. So we need to be able to do these 6 things. So I'm going to walk through them briefly first to kind of briefly explain them. Then we'll dig into them a little bit deeper. And then we'll look at BAD ASS HVAC and how it actually can deliver these things. But before I get there, I want to address the elephant in the room because we have a virus that has changed all of our lives, sometimes for the better, oftentimes for the worse. But I was very pleased to see this tweet yesterday. So Twitter has a couple of really good areas. Like it can be a train wreck in a lot of ways, in a lot of subjects. But energy Twitter and air quality Twitter are both very, very good. And if you want to watch just what's going on, this is the place to be. So Dr. Kimberly Prather here, she posted this video that was Dr. Fauci talking about a few things, namely he's talking to people about aerosols. So aerosols are very small particles. It's generally under 5 microns. And that's where, well, it's under 2.5 microns is where it gets to our lungs. Under 1 micron is where it goes to our blood. And there's a lot of previous research done, namely by Dr. Lindsay Marr, who's mentioned there. Like it's a small world. Dr. Marr did a study to see what the size distribution of the little spit particles that we release when we talk or sing or cough or sneeze, to see what size they are, and a lot of them are small. So it's looking more and more like probably the majority of the spread of COVID-19 is airborne through the air. And so I love seeing this tweet. She is talking to Dr. Fauci tomorrow, and we're probably going to be hearing a lot more about aerosols moving forward. So it's this very small particles. This is where filtration is important. And of these 6 factors, the 2 that are looking most important for COVID are filtration. So you want to be able to filter those little particles out, the aerosols out. And fresh air, you need to be able to dilute the air. The target is 600 to 800 parts per million of carbon dioxide. And outdoor level is, 400, 450, maybe 500, depending on where you are. And so you want to be able to add enough outdoor air. This is very challenging in commercial buildings because there's a lot of people in a commercial building, where in a house, typically we've got 2, 3, 4, 5 people, something like that, in a relatively large volume. So it doesn't take as much fresh air residentially, which we'll get into. But these are looking to be the key factors for controlling it. Number 3 and 6, which are both dealing with humidity. The dehumidification for COVID-19 doesn't seem to matter as much as it does for most viruses. It's usually a big deal with viruses, but we're seeing plenty of spread in Florida still, which is a very humid climate. So it doesn't seem to matter there. Maybe it will matter somewhat on adding humidity, so you want to be able to humidify. But thus far, the early work is looking like the humidity control is not critical. By the way, I did an entire webinar on this back in March, and I'll give the link to Brett so he can post that. So I dug into the research that I could see, and now I'm not a true expert on this. Like I've dug a lot into it, but I definitely don't have a degree in it. Okay. So now that the elephant in the room is addressed, and I'll touch on it briefly as we go, let's go into the actual details here. So 6 functions. Every car that has air conditioning and a cabin air filter, which is pretty much everything built since 1995 or 2000, can do 5 of the 6 functions of HVAC. So how many can most houses do? And that's nice to give this in front of a crowd, but I can't hear you all, so I'll just answer it. It's a rhetorical question. Most houses can't do any of the 6 functions, at least not well. And that sucks, which means that your car HVAC is drastically superior to your home HVAC. It's maybe 1% of houses out there right now can actually do the 6 functions well, but we're going to talk about how to do it. So first piece is load matching. And here's what that looks like. So in your car, you can dial in, do you want a little bit of heat, a lot of heat? Do you want a little bit of cool, a lot of cool? I mean, once you start the car and it starts going down the road and it comes up to basic temperature or down to basic temperature and cooling season, you can adjust it, and what you do is you match how much heat or cool the car is putting out to how much it needs to keep it comfortable. In a house, you can't do that. It's 85% of existing HVAC systems on the market are single stage, which means they are either on or they are off. So there is no control. You can't match what it needs. So the biggest thing that this leads to is, say when it's 50 degrees outside, so it's cool, but it's not cold, there's very little load. The house doesn't need much. So if you notice your house feeling very cold when it's 50 degrees outside, the odds are that your equipment is drastically oversized. And in general, we find equipment to be between 2 and 4 times larger than it needs to be when we do a load calculation true to both blower door and energy use. So we do a real load calculation, not a guess, like this is a scientifically based load calculation. Second thing that cars do is filtration. They have the cabin air filter, so that filters the air coming in and then also some going through the cabin. They can do dehumidification, which looks distinctly like the air conditioner button. So anytime that you want to dry your car out, you can push the AC button. So even if it's 50 degrees outside and it's starting to fog up, you can hit the AC button, or oftentimes you'll put it on defrost and that kicks the air conditioner automatically. So you can do that in your car, but your house, you don't have a lot of luck with that. Only when the air conditioner is on, and really only once the air conditioner has been on and running for at least 10 minutes. And if your system's oversized, it may never run for 10 minutes before it shuts off. Only then do you get dehumidification. So humidity control in houses in general is not just terrible, it's abysmal. Next thing is fresh air, which is simple enough. You can see down here, that's the recirculate button, that's the fresh air button. So every car has that built in. They can do mixing, so you can put the air where you want it by directing it. The only thing that they don't do is humidification. There's no way to add humidity. So that's the basics. Now let's dig into these a little bit deeper. So load matching, let's see what that actually looks like in practice. So again, that's what the house and car look like now. This is out of the sizing chapters. This is not one of the free chapters of the book. This shows what you normally see. So when equipment is oversized, the temperature goes up very quickly, and then if the house is leaky, it goes down very quickly. And when you have a house that is poorly balanced, or you have rooms that are particularly leaky or not well insulated, it's not uncommon to see 10 and 15 degree differences from one room to another. And that's what this is showing. This is an uncomfortable house, so the temperature is racing up and racing down. This is not what you want to see. Ideally, when you match load and you put out just a trickle of heat or a trickle of cool to match what that house needs at any given moment, and you balance how much heating or cooling the different rooms of the house are getting, or you seal it up if one part of it is particularly leaky, you get this, where the house moves very slowly and the rooms are very close to each other in temperature. Ideally, when you walk from one room to the next, you shouldn't feel a difference. This was fun with a new project that we did with a client. I asked him, so which rooms in your house are different temperatures? And he thought about it. He's like, none of them. And he thought about it some more. You know what? The 2 guest bedrooms I haven't been in yet. I'll go check them. And I asked him what I got there, and he's like, no, they're the same. So that's what you want. You want the house to feel absolutely the same everywhere. Difficult with existing homes, but you can usually get things within 2 or 3 degrees. Another really important thing here is what's called mean radiant temperature. It's getting the surface temperatures of the house to all be really similar and also be close to what the thermostat says. So if your thermostat says 72, you want all the surfaces in the house to be between 70 and 74, because most of our comfort, we're actually sensing the surface temperatures around us. We have over 150,000 sensors in our body for that, where our house usually has one temperature sensor, the thermostat. Now, what this looks like in practice with actual HVAC equipment, this is kind of a typical house here that we find in Cleveland, which will shock most people, because the smallest furnace that you normally will see is 60,000 BTUs, where a standard air conditioner or heat pump is 36,000, or it's also known as 3 tons. Every ton is 12,000 BTUs. So very commonly, we will walk into a 2,000 square foot house and it will have an 80,000 BTU furnace. That is the wrong size equipment all of the year. So red here is that it's oversized, it can't match. And the blue is where it can match. So that 80,000 BTU furnace, it is wrong all year. It is never the right piece of equipment. When something is sized well, it shouldn't shut off when it's a very hot or a very cold day. Now, if we do, say we right size that and we put in a 3-ton single stage heat pump, then in theory, we can match it about 1% of the year when it's cold. So this is squishy. I understand the vagaries of heat pump output, but let's just say they do 36,000 all the time, or view it like a furnace. It's gonna be wrong almost all the time. If we do a 2-stage heat pump, now we can get to maybe 30% of the year where we can come close to matching what the house needs. But if we really want to get there, we need to go to a full modulating piece of equipment, which we're going to come back to again. And if we really want to do a good job, we actually undersize the HVAC. So we put a 2-ton in, and for heat load, when we can't make up for it, we use resistance backup. And that may sound utterly terrifying, and trust me, for the first couple that we did, it was, but it's not that bad once you get used to it, but you need to trust your load calculations. So I want to pause here for one quick second because sometimes there's questions. Let's see, Monica. So we use a couple, but for the basic ones, we use a program called EDS Auditor, and you can run a decent load calc in about 5 minutes.
So that question is just what load calcs do you use? Is that what you're saying?
Yep. Yeah, I'm just looking at questions real quick. And Ian, yes, load matching will definitely achieve better comfort in a leaky house, but it's still going to be problematic. So I mean, view it like a boat that's leaky. You can upgrade the bilge pump and upgrade the engine, but you're still going to be struggling against that water coming in. Scott, I see you use RightSoft from ManJ. So RightSoft is a wonderful program, but if you don't enter blower door in, it can still be horribly inaccurate. And there, Michael Collins, is it critical to always run a blower door test to calculate load? Well, that depends. Do you want it to be right or not? If you don't want it to be right, don't do it. Without a blower door, we find that load calcs are easily plus or minus 30,000 BTUs. And keep in mind, like, we're finding loads consistently in Cleveland for 2,000 square foot homes and under. This is a cold climate that are under 3 tons. So you are plus or minus a piece of equipment without a blower door. You can use energy bills, which helps some, but if you want to size aggressively and be comfortable, I don't know how you do it without looking at prior energy bills and the blower door. I just don't know how you do it. I wouldn't want to put money on it. You're taking a risk. So hopefully that helps. Let's see, I think that's it for the moment. Oh, no, there's a couple more. Jake, yes, resistance heat runs at the same time with most heat pumps, not all. It depends on your thermostat. It's more of a control thing than the equipment. And Lars, hourly or daily load simulation calculations, not really. I mean, they're built into the more advanced calculations. The simple ones, they're simple. You're just trying to get a good idea of where you're going. If you're going to do advanced load calcs, then like RightSoft is a nice program for that. Very complex, not an easy one to learn, but it's a very powerful program. All right, better keep going. If I missed your question, just come on back and hit me later when I stop. All right, second function, filtration. This one's pretty fast. So the better the filter you have, the better job it does in taking out the very small particles. Again, the stuff that gets into your lungs and into your bloodstream. This is a chart that you can just look up filter types on Google and it will come up. Note MERV 13 here, and notice right here, virus carriers. This didn't come out because of COVID. I've seen this chart out for a decade. We've known for a long time that the very small particles can get caught. It takes a MERV 13 or higher. This is still not perfect. This will knock out about 75% of the viral particles that are in that ballpark, the 1 to 3 micron range. Doesn't necessarily do a great job under 1 micron. Sometimes it does. So if you really want to do a good job, you need to move to like a MERV 16. The problem is every time you go up here, you create a bunch of extra back pressure. And if you aren't careful, you can kill the motor in your furnace or heat pump in a couple of years. I've seen them fail in 18 to 24 months when somebody put the wrong filter in. So that's a critical thing. But you want good filtration. There's all kinds of reasons to do this. You don't make your body be the filter for the garbage in your house. Let the filter do the work. All right, dehumidification. Oh, sorry, yeah.
A quick question. On existing homes especially, I assume if you get thicker filter boxes, are those going to have less of that resistant airflow problem that you mentioned versus the thinner ones?
In fact, I'm going to show numbers in a slide later.
Okay.
Yeah, that's a good question. You have to run 4 and 5 inch or 6 inch media filters to get the resistance low. I just tested one yesterday where the filter by itself was creating 0.7 inches of water column of back pressure, and the whole system isn't supposed to be over 0.5. The filter alone was creating more than that. That system, it was noisy, and he's going to be replacing his fan motor soon with that kind of pressure. So yeah, it's important. All right, dehumidification. This is the biggest piece of this presentation because in doing air quality monitoring, we have about 40 FUBOT air quality monitors out in the field right now running. And if you don't have humidity control, you do not have control over air quality. You don't have control over chemical pollutants. There's all kinds of things that you cannot control. So Mitsubishi, I'm sorry, I know you sponsored this. Can you guys add the dehumidification feature that I'm asking for here? Because you can't do BAD ASS HVAC with Mitsubishi equipment right now. Cannot, period. I'll make fun of you if you call it badass. So let's dig into what that looks like. So again, we don't have much control in our house. We can't do 24/7 dehumidification, not with the central system anyway. And here's where and why it's very important. So this is an ASHRAE chart from the mid 80s, if memory serves, yeah, 86. Take a look at the second line here, since we all have viruses on the brain right now. If you get to very low or very high levels of humidity, then viruses tend to spread a lot better. So ASHRAE shows 40 to 60% as the ideal range. We strongly think that it should be 30 to 50. You don't want to run 40% in a cold climate where you're going to get condensation and then mold somewhere. It's too high of a range to run when it's, say, below freezing. Definitely when it's below 10 degrees. But anyway, viruses are important for controlling there, but this whole optimum zone between 30 and 60 is kind of a good place to live. Notice on the bottom here, chemical interactions. This is the only one that's one-sided. Well, I guess ozone is the other way. But as relative humidity goes up, the VOC interactions increase. This is why when you get a humid day, you remember where the dog peed in the corner that you didn't fully clean up. That's the kind of thing that comes out. So controlling humidity both on the low side and the high side is really important. Low side's pretty easy. We'll get to that. It's just a humidifier. It's an inexpensive piece of equipment. Controlling humidity from getting too high is really difficult. And I will just touch on a little bit of the technical side here. So what we have is a problem of sensible versus latent heat. Sensible heat is heat. So that's what you think of your air conditioner mainly doing. And latent heat is humidity. It's actually phase changing it from vapor to liquid. And the challenging time that we have is pretty much everywhere in the country. We have 2, 3, 4 months of shoulder season where we get 75-degree days, and I should say East Coast. So this is a humid climate problem. If you're in California or somewhere where it's a dry climate, you don't have to worry about this very much, but we really do here, and it really complicates our work. So if it's 75 degrees out, but it's very humid, it's a 70-degree dew point, that's extremely difficult because the air conditioner has almost no work to do, but there's a ton of dehumidification that needs to be done. In fact, this weekend, we just had all that happening. It was 72 with a 70-degree dew point most of this weekend, and it just didn't feel good. We've been running windows open, and I was tempted to kick the AC, but I also knew that it wouldn't matter because it can't do that. Now, here's what that might look like. So here's relative humidity in a client house where this is September of last year. So this is a shoulder season here in Cleveland. You can see that his relative humidity was over 60% most of the time. But here's the critical thing. If we look at it as dew points, he is over 55-degree dew point, all but this little bit right here. 55-degree dew point is where you want to stay under. And easiest way to think of dew point is it's where the air is full. So if you see a can of beer or a glass of lemonade that's beating up on the outside, that means that the surface of that glass is below the dew point of the air that it's in. So you have a dew point indicator right there. But this house, thankfully, is an older house and has older building materials, which aren't as moisture sensitive. But new houses, if you run them this way, it can be problematic. And even if it's not super problematic in the house, so this is the dew point calculator, which was originally developed for art preservation. But take a look, here's that condition that I suggested, 75-degree temperature, 70-degree dew point, which is very humid. That feels like you have to cut the air with a knife. Days to mold, the risk there, 8 days. So you need to have 8 days continuous of that condition to get mold, which may or may not happen. But, so if that's upstairs, what about in the crawl space or the basement, which is connected to the ground? The ground is usually somewhere between 50 and 60 degrees. Now that basement is below dew point. Look at the days to mold the risk, 2 days. That's not good. So how do we deal with that? We dry it out. So if we get to that 55-degree dew point in that same 68-degree basement, now there's no risk. So you need to be able to manage the humidity of the entire house to be able to do this well. And there's lots of crawl spaces there, just nasty, nasty, nasty out there. And plenty of basements too. So how do we deal with this? Remember, we don't have much cooling that we need to do, but we have a lot of dehumidification. So the fix is what's known as reheat dehumidification, or just reheat for short. And the concept's really simple. This is very common in commercial systems. It's very uncommon in residential systems, which is actually the main reason that I wrote this presentation, was so that I could badger manufacturers into adding this to their controls, because it's a software problem. It is not a hardware problem, as we'll get into. So here's what happens. We have that 75-degree, very humid air going into the air conditioner coil, and then it gets cooled off. So now it's cold and dry. 95% may not look dry, but that's like the 50-degree dew point. That's quite dry. But you don't want to blow this back into a house when the house is already basically at the temperature that you want it for cooling. So you need to add heat back to it. So out the other side comes comfortable air at 70 degrees. That's very, very dry now. That's how you want to do it. There are two methods to do this. You can do what's called hot gas, which is where you take the refrigerant that is now hot from running through this coil, and then you run it through another coil. There's one manufacturer out there that does this. It adds a fair amount of complexity, and I have suggested it to a couple of contractors that use that particular brand, and they ran screaming for the hills. They were afraid of it. And I largely agree. It can add more complexity than I would like to add in a residential system. because we basically have to assume zero maintenance. That's the safest assumption. The other option is we can do electric reheat, and our preference is by far electric. So I'll show you what that looks like. So here's a typical heat pump. This is an upflow, so the air is coming through here. So the coil is on the bottom, and then you've got the fan, and then up top you have the heat strips. So this is really standard, like particularly if you're in the Southeast, the odds are you have a system just like this in your house. The nice thing is those heat strips, it's about a $200 part, and it's almost always there anyway, being installed with one of these systems. So it's a really inexpensive adder that is already part of most systems. Now, the first objection that I get, and the main objection I get to reheat dehumidification is, oh my goodness, it is not efficient. You're adding resistance electric and it's going to cost a fortune. We're all going to die. No. We'll get to the actual numbers on it, but let's look at the alternative first. And this is an alternative we use. This is a whole house dehumidifier in one of our projects. You can see my manometer sitting on top of it, checking the static pressure of that system. And I have one of these myself. Now, these are really nice, but they cost $3,000 to $5,000 installed to do a whole house dehumidifier. Coincidentally, if you're looking at a cheap single stage furnace and air conditioner versus a high-end heat pump or furnace or whatever it might be, like a full furnace and air conditioner, furnace and heat pump or heat pump only system, the cost difference between that crappy single stage system and a high-end system is usually about $3,000 to $5,000. So I would really like to have that money and put it that place instead of in putting in a dehu. But that said, this is a nice piece of equipment, and if you have new equipment and you have humidity control, this is oftentimes the answer. But I'm thinking about putting another piece of equipment in. Now, important note, these things use a good chunk of juice too. This one is remarkably efficient. So this is mine running in the basement of my old house, and it's pulling a little shy of 800 watts. So it was using 4, 5, 6 kilowatt hours a day. And that was just doing the basement. That wasn't doing my whole house at that point. But they use juice, so it's important to note that. Now, here's what the resistance coils look like on full fire. So this is 15 kW strip heat running. And then let's look at what the actual cost of. So this is what the manufacturer that we like using the most, and they do energy tracking on board. It's not perfect, but it's pretty good. You'll definitely have a good idea of what's going on. This particular client used 151 kilowatt hours. So if you assume 10 to 20 cents per kilowatt hour, that's $15 to $30 a year. This is not an expensive thing. My dehumidifier in my basement was using that per month easy. Now, that's a low house. Let's look at a more standard one. This is the 1900 house of the future. This is one of our electrifications. So he's using a decent chunk of reheat. He's using about $90 a year of reheat dehumidification, but still not a huge deal. I mean, it's probably similar to what the dehumidifier itself is going to use, maybe a little more, maybe a little less. This is the worst one. This was a new house that we did where it was unoccupied for a while, and I didn't think they were going to set the thermostat as low as they did. So the house was still wet from the slab drying. So I got a phone call for $130 or $150 electric bill when they weren't there, and it was the reheat doing it, but it was a setting problem. I had set it to 46% relative humidity, and that was too low for 70 degrees. It would have been fine at 75. In fact, it was, because you can see 2019 on the electric reheat line, 0 kilowatt hours. So anyway, this is a standard thing. Again, most heat pumps out there already have this capability. They have the physical equipment. They just need the programming to do it. So hopefully that makes this less scary. Like, we're not talking a fortune in energy use for doing this. I mean, you got to watch your settings a little bit, but this is very doable. So I don't know if I'm supposed to really mention all of these, but these are the current residential options. So Carrier Infinity, the Trane American Standard 824, and the Honeywell IAQ. That's it that I know of right now that will do reheat. So badger your tech reps, please.
Nate, you had mentioned a $200 ad. Now, are you saying, like, when you go to buy the product, it's one of those things you can add it on for $200, or is that $200 you can add to any kind of system out there?
It needs to be a heat pump system that has a slot for the resistance strips. But any unitary heat pump system that's out there, so you can't do that to a mini split. Some of the ducted minis will do it, but the ductless don't have a place for resistance. But most heat pumps out there that you can connect the duct to have that ability. It may or may not actually have the strips in there.
And traditional air conditioning systems don't have it.
Correct. Although you may get what's called an electric furnace, which would be an air conditioner with resistance backup, or resistance actually as the heat, which to me is asinine. Like you can have it cost 2/3 less by just putting in a heat pump version, which costs like $300 or $500 more wholesale cost. Like, it's crazy not to do that, but that's out west when you got 7-cent kilowatt hours, you do that. All right, let me see any questions here. We're pausing. Closed ionic filtration. Donald, I'm not enough of an expert on that to be confident in that. But generally, my view is don't add anything to air except for water. The ions and some of the stuff that I've seen, they create clumps of dust particles, and I've had several clients note that their house got dustier after they put one of those in, which is the opposite of what we want to do. Filtration can usually look better there, straight. Please post the HVAC load calc software. Yeah, so Brett, that's a question for you. It's EDS Auditor, and remind me if I forget to let you know what that is. Separate compressor, dehumidifier, Donald, no, generally not. You can, that would be the whole house version, but this is, the whole point of BADASS is to have it be one pretty simple system. The controls are complicated and the equipment itself is complicated, but the install looks basically just like what people are used to doing. It looks like a traditional furnace or heat pump install. Okay, fresh air. This is an interesting topic with COVID right now. And I could have changed this, but I didn't. In fact, this whole presentation, the only thing that I changed to it was adding the 2 slides mentioning COVID after that hit. So there's a big question of how much fresh air do we actually need? And this is an interesting challenge because you need a separate piece of equipment generally to provide ASHRAE 62.2 levels of ventilation. We'll get to that in a moment. So for starters, this is a study from Lawrence Berkeley National Labs that basically found that high levels of carbon dioxide make you dumber. That's the short layman's version. So it's good to keep your CO2 levels lower. When it comes to COVID, the recommendation is 600 to 800 parts per million to stay in that range. And so that comes with a bunch of other good pieces. So if you're falling asleep at work, if you get a CO2 monitor, you may find that the CO2 levels are too high in there, and you want to add fresh air. So, but let's give an example, because this is interesting, having done a bunch of air quality monitoring ourselves. This is an event that we did February of last year in one of our electrifications. So there were 35 people in this house. And that, I think we can all agree, is pretty unusual for a house to have that many people in it. And I didn't design for that kind of thing to happen. But let's look at the events. This is from the FUBOT air quality monitor, which sadly is not available anymore. So this is monitoring TVOCs, total volatile organic compounds. This is not specifically carbon dioxide, but this sensor is very cross-sensitive to carbon dioxide. So if the levels are high, it could be CO2, it could be other things, but if the levels are low, CO2 levels are low. You can assume that. So this house had 30 cubic feet per minute of fresh air coming in using the system we'll show in a little bit. And that's about half of ASHRAE 62.2. So this is at the beginning of the presentation at 5 o'clock. You can see the spike beginning. That's the top of the spike at 7 as everybody was starting to leave. And what I thought was wild here is not that long later, it was at 7 hours later with just 30 CFM, that house was back to normal as far as air quality goes. So it was back to having the normal 3 or 4 people in it. So this was surprising, and we've seen this again and again. It doesn't take a massive amount of fresh air to keep CO2 levels reasonable, as long as you're talking normal family sizes, 3 to 5 people. Commercial buildings, again, whole other story. Another piece of the fresh air that I should mention before we move on, this is the filter from the ventilating dehumidifier I pictured earlier. This filter, if you look at that top left corner there, how it's quite dark compared to the yellow everywhere else, that is where the fresh air intake, quote unquote fresh air intake, hit the filter. This filter was only 6 weeks old, and this house is quite close to one of the freeways in Cleveland, about 1,000 feet away. And I was shocked at how dirty that filter was after that short of time. And a lot of that is probably what I have in the picture there of exhaust. So that's probably a lot of diesel and car exhaust getting stuck in there, maybe brake dust. But regardless, it's a bunch of stuff you don't want to breathe, and it's not that hard to filter out with a decent filter. But fresh air ain't fresh. Okay, so how much fresh air do we need? We definitely need some. So I will never argue against that. You always want to bring in outdoor air, but we may not need 62.2 levels. If you want to add more, you can always add a separate system like an ERV or an HRV. We don't generally like them because they tend to not get serviced and they fail. And then no one knows because there's no air quality monitor. So the nice thing about the system I'm going to show is the fresh air will always work as long as the system is working. So unless the heat or air conditioning is off, there will be, well, actually, as long as it's broken, there will always be some fresh air coming in. If you want to bump them more, you can do other things, but make sure you service those filters. There are a lot of them that die very early because they never get their filter changed. And as you saw, the filters get dirty. Okay, right place at the right time, or I just call this mixing now. Think of a house, if you've got a house that's 2 stories, you've got the basement, the first floor, and the second floor. I'm biasing to the Midwest where we have basements. But that's 3 different levels that you have to keep at a relatively similar temperature. So think of your house like a vinaigrette with 3 layers instead of 2. How do you keep a vinaigrette from coming apart? You stir it a lot. And so you can do that with mixing basically with the air handler. And the last piece is humidification. So if you're out, probably a dry climate all the year. And then here in Cleveland and most cold climates, it gets quite dry, particularly in leaky houses in the wintertime. And again, we want to control that so that we avoid the bottom end of this chart. So that's the explanation. Soon we get to dive into what it looks like, which is awesome. So recapping, there's the 4 buckets. We need to be able to control moisture, dust, chemicals, and combustion. And this is how we do it with the 6 functions of HVAC. So load matching, filtration, dehumidification, fresh air, mixing, and humidification. And again, a lot of this stuff and then a bunch more is in here. For anyone here that is a pro, you can go to my website, download that, and you can share that for free with no attribution. If it's helpful to you, please use it. I wrote it to be helpful for the industry. Okay, so now we finally get to dig into what BADASS is. Now that we've gone over the why, we can do the how. So it does stand for something. It's Big Air Drop Air Source System. Thank you to Eric Kaiser for figuring out the air source system. That wasn't me. And thank you to Michael Hausch for figuring out Big Air Drop, or it's also Big Ash Drop is the PG-13 version. And so here's basically what it looks like, and then I'm going to walk you through pointing out what's here. And thanks to Michael Hausch for doing this graphic. So for starters, we have what we call the BAD. I posted a picture of a project that we'd done that had one of these filters in it, and it got coined a Big Ash Drop, and henceforth it shall always be known as that. So we just figured we'd run with it. And here's what that is to anyone that's not familiar with that. So the drop, it's called the return drop. So this is in a basement. This is the return air coming down. It turns here and then comes back up in the furnace. Think of air like water, because at the pressures that it runs in an HVAC system, it flows just like water. So imagine if you were putting water through this and you asked it to slam to this corner and turn and come back up. Is it going to be happy? No. Creates a lot of turbulence, a lot of pressure. It's not a good thing. So we want to avoid that. And this is one of the electrification projects. So to fix that, all you need to do is increase the size of the drop. It's just a bigger duct. And what we find is you size the duct, you can just make it square, and you size it the same size as a filter. So here's the media filter. Brett, you asked about the thicker filters. Here it is. We always use media filters. I don't really care what brand. They can all work just fine. But a nice thing about putting the filter here is it comes down here at pretty low velocity. Low velocity is better for filtration. You don't want to cram the air through the filter. You want to let it slow down and take its time. And then it also hits the whole surface equally, or nearly equally, much more so than if you put it down here. And back to the filtration, now using a MERV 13 or a MERV 11 is not a big deal. So MERV 11 is our general minimum, but with COVID, you want to use at least a 13 higher if you can do it. Now to keep the air happy, it's nice if you do curves here, although I've been genuinely surprised if you just make this stuff really big, the air figures it out and the pressures are quite low in the system. I've been just surprised. There's nothing like going out and trying stuff and measuring. You learn things. So here's one example. This is in a condo. So this is actually a downflow system. The return air is coming from here and going down. This is the filter. And this filter is only running 0.04 inches of water column of back pressure. These are usually rated at 0.1 and nobody ever gets 0.1 out of them usually because they install them someplace where they're not happy. So this is insanely low pressure drop across the filter. And it's all we did was upsize this duct right here, and that made everything better. So very, very simple near equipment changes can make massive changes to the airflow and the comfort in the house. And you're talking, a couple $100 in parts tops and a couple hours of labor extra. So it's not a huge deal. And the magic of this, so this is the piece of equipment that we like using a lot. Note how much juice it's using, 17 watts. If you look at an ERV fan, they're usually going to use somewhere between 15 and 40 watts each, and there's two of them. This is the air handler. This is the main system. On low, it's pulling 17 watts, and I have yet to see one over 40, even on the 4-ton units. So if you do a good job of keeping the static pressure low inside the systems, you can really get very low draw. And so what you get with low static, you get low usage, you get mixing for free if you leave the fan on all the time. And then there's one more piece. So the last piece of the BAD, and not everybody's going to do this, but this is a smart thing to do, is a duct to outdoors. So this S curve small duct, this is going from the return to outside. In this case, it was going through a basement wall. And then there's a little motorized damper here that you set to close at very high or very low temperatures. And so what you get when you do that stuff right there is for somewhere between $2 and $10 a month. So at 13 cents a kilowatt hour, it basically works out to, or 17 watts is $1.70 a month to run that 24/7. So for $2 a month, you get much better health and air quality. You get fresh air, you get mixing. Who here is okay with that? I'd love to see you raise your hands, but you better all have your hands in the air. This is very, very cheap for providing remarkably healthier and more comfortable homes. So a buddy of mine suggested changing the lyrics to this song. So I like big ducts, and I cannot lie because it requires big ducts to do all this, but the tin is cheap. It's just not that expensive. There's a bunch of different ways to do this, so I put these in here as just showing some variations. So you can do turning vanes. This is my buddy John Summelhack being funny. Elbow with vanes versus elbow with vanes. So these are turning vanes in here that turn the air. So if you don't have a lot of space, you can install turning vanes to get the air to do what you want. This is another product that you could use, which has a filter at a 45-degree angle inside of it. And so you can use that for a system like this where you don't have much space, because it's difficult to increase the size of this duct with this water tank here. So, you're going to have practical in the field problems. Although you could potentially, move that system over, but there's different ways you could do it. But point is, BAD ASS HVAC is meant to be flexible. It's not totally rigid. It's more of a whole bunch of best practices pulled together. A pattern language, I've heard it called. So the BAD, we are huge in offer decline. So if you are a professional, offer it to everyone. If they decline it, then it's on them. And do it by email or something like that where it is in writing so you can point back to it later. Okay, so the BAD, that handles 3 different functions of HVAC. So that gets filtration, fresh air, and mixing. But it only does 1 of the 4 buckets. So what about the other 3 of both of these? This is where you don't just need a BAD, you need BAD ASS HVAC. So now you need to add the air source system side of things. And this is where heat pumps are phenomenally helpful. This has surprised us how much we end up using these. So if you want to have that load matching, like we were talking about, where all the rooms are within a couple degrees of each other, you need to have right size multiple speed equipment, preferably very aggressively sized, like that 2-ton. The more aggressive you can get, the better. And that's best done with a modulating inverter heat pump. There's every manufacturer makes a number of these. And how we learned this, because the first question we get is, I live in a cold climate, there's no way that heat pumps work. So this group is probably largely used to seeing these things work, but this is how we figured it out. This is my partner Ted's house, is actually his mom's house, and they installed a hybrid system, a 60,000 BTU furnace with a 3-ton heat pump on top. And this was about 10 years ago. This has been a while. So there's the outdoor unit. And so they put it in, and Ted got a phone call from his mom. Hey, Teddy, everything's okay. The house is heating, but the air coming out of the vents is really cold. And it was about 5 degrees outside, which is design temperature for Rochester, New York, also actually Cleveland. And he instantly thought, oh, they didn't tell the thermostat that the furnace existed. So it only thought that it had a heat pump to work with. So that heat pump, a 3-ton heat pump, was heating a 3,000 square foot, 30-year-old home down to 5 degrees. And he's like, so why are we doing furnaces? This is stupid. And that began the whole thought process of electrification. So here's screenshots of energy use of a bunch of our all electric projects. So we have done a bunch of these. So if you think that heat pumps don't work, for starters, the first 4 that we did in cold climates were all Century homes. So they all got shell upgrades, but you can definitely make it work. So here's a bunch of projects we've done. So there's a 1900 house, a 1918, a 1900, 1890, 1960s ranch, 1960s split level. That was the one where the Electrify Everything event was, and you can see she's got solar on her roof. Another split level that we did. This is a quite new house, and that one is running beautifully. This is a house that we pulled an oil furnace out of and changed to a heat pump. This is a condo. And then this is one of our most recent ones where the house got an addition and we made a bunch of changes to the duct system as well. These things can work. Here's a whole bunch of existing homes in Cleveland, and almost all these are 2 or 3 ton. The new house, we put a 4 in because we weren't familiar with that piece of equipment yet, and we could have done a 3. It would have been fine. I wasn't gutsy enough yet. So BAD ASS is a BAD plus the modulating inverter heat pump that we already talked about, and heat strips for reheat. And if you size aggressively, those will also cover you in your very cold temperatures. And then also a humidifier for climates and clients where that makes sense. That needs to be controlled by an outdoor temperature sensor, because the humidity really needs to get dialed down when it gets very cold outside. So when it gets below 20, you want to move the dew point inside the house to not be a whole lot higher than 20 degrees. or else you're going to get all kinds of interesting problems. And if you have a mold sensitive or chemically sensitive client, you may want to be careful with central humidifiers, but for the vast majority of people, they're a really good solution. So to tie all this back together, here are the 6 factors or 6 functions of HVAC overlaid into here. So the first one is load matching, which you do with a heat pump. Second one is filtration, which you do with a big media filter. The third one is dehumidification, which you do with the resistance strips. Fourth one is fresh air, which comes in through the scuttle. Now these scuttles, they don't flow a ton. They're usually going to flow between 10 and 40 CFM, depending on your fan speed and static pressure. So keep in mind that if you're going for 62.2, you probably need to have a bath fan in there extra to hit that with that, or you could do an ERV and HRV, although beware when you pump a bunch of outdoor air in, particularly in humid climates, you can really outstrip the dehumidification capability of the system. Ask me how I know that. Mixing is done with this great big drop, so you keep the static pressure low, and then again, the humidification. So we've got all those pieces together, and it's really one piece of equipment. It's just one modulating heat pump. That's what works best. You can do this with a furnace, but you have to have separate dehumidification. And now we have tackled all 6 functions, and we have done it well. In fact, we've done it better than your car because we can humidify. So take that, car. And then another cool thing about this is, yes, we tackle the first 3 buckets of air quality, but the 4th one, combustion, we just eliminated. So we don't have to worry about it. And personally, I hate combustion safety testing because fixing it is usually a pain in the tuchus and it's expensive. And I would much rather clients just do something that doesn't burn things, and then I don't even have to worry about that. I don't need that to keep me up at night. Different variations, yes, you can put this in an attic, or this would also work in a crawl space. Soon enough, my house will finally be getting this. I have been the shoemaker with barefoot children, and I'm really looking forward to having Bad Ass HVAC in my own house. And you can also do it, like I said, with a furnace. So here's a nice furnace and a modulating heat pump on top. But if you're going to have good dehumidification control, because you can't do reheat, you can't pump heat into a coil when you're trying to cool it. You have to do a separate dehumidifier. And again, that's an expensive rig. The fellow that I talked about couldn't figure out what rooms were different temperatures in his house. He did this in his house, and we were genuinely surprised that he opted to spend an extra $5 grand to do that. So closing, elements of Bad Ass HVAC. These are the 6. So if you're going to screenshot something, this may be one of the best things. And then in my closing slide, it'll have a bunch of resources and then the 1 through 6 on the thing as well. So the 6 things are load matching. You need a right size variable speed piece of equipment. Filtration, you need at least a MERV 11. With COVID, you need at least a MERV 13. Dehumidification, you need to be able to do reheat or have a separate standalone. If the manufacturer you use doesn't have it, please annoy the hell out of them. Say, I want reheat dehumidification, just add it, Nate said so. 4th thing's fresh air, so you can do a fresh air duct. And again, that will work as long as the HVAC is working. It's not gonna fail and no one knows. Mixing, you do a big air drop. Humidification is really important, again, to do that with one that has an outdoor temperature sensor. So don't use a dumb humidistat that's just right on the unit. That needs to plug into a smart thermostat to do that. And again, if you don't have all 6 of these, don't call it badass or I'll make fun of you. So you need to figure out the dehumidification thing. That's the hard one. Go put in some air quality monitors. You will learn what we have learned. Holy crap, I can't control the air quality in the house unless I can keep the humidity low. So that's that. Now, the other elephant in the room is that 85% of HVAC out there is single stage in homes. So how do we change that? And we don't have time to dig into that. Plus, I would have to do some selling. So what you want to do is look for the HVAC 2.0 advanced discussion group on Facebook. We talk a lot about how we can match people's goals, house needs, and budget to find a project for their house that's likely to work. So this is for HVAC pros. You need to at least have some experience with HVAC to join there, please. professional experience. You know, you could be a designer, because I don't actually do the HVAC. I just specify it and commission it. But that's not really for homeowners. If you're a homeowner, look up the Electrify Everything group, and there's lots of discussions there to be had. And again, you might want to go download that to use for you or your customers. And that's what I've got. I have not been watching time. Hopefully I'm not way the heck over.
Yeah, no, we're good. And we got some questions coming in. Can you stick around a little bit, Nate?
Absolutely.
Yeah, great. Well, before we get to those questions, I just want to real quick, here we go. And there I am. For those of you listening live, check your inbox for the certificate and take that survey. It'll pop up too when you close out as well, so we'd love to get your feedback. For those of you watching this in the future on demand, make sure to take that 10-question quiz, get an 80% passing rate, and then you can pick up your continuing education that way. And then, where are we at here? We're stuck. There it is. Oh. And then real quick, for those of you looking for that quiz, click on the YouTube link on our website or on our YouTube channel. Click on Show More beneath that, and then on the right side, click on the quiz access link for CEUs. And again, before we get to those questions, a huge thanks to our board of directors, all of our volunteers, and our top tier sponsors, Mitsubishi Electric, Build Equinox, CRV, and then Rheem for air source heat pump systems. Nate, so there's a question that came in, and it's on my mind too. We didn't hear you mention anything about duct sealing. We know that there's some easy do-it-yourself ways to do it, all the way up to much more advanced ways to fully seal our ducts. What are your thoughts on duct sealing, and how does that fit into the BAD ASS HVAC concept?
So it's the classic answer to everything building science, which is it depends. So here in Cleveland, our ducts are almost entirely inside the house. I'd imagine where you are in Michigan, it's the same thing too. So if the ducts are inside the house, I'm not necessarily super duper worried about it. It can be a nice thing to do, but you also want to see if the system has enough static, because you can seal the ducts, drive your static up, and you just paid $600 to seal your ducts to kill your air handler motor 2 years later. Congratulations. If you'd left it alone, it wouldn't have died.
Right.
So it can be nice. It depends. That would depend on the project. Now, if you are down south and you have ductwork in the basement, well, not so much the basement, in a crawl space that is unconditioned, or in an unconditioned attic, you really want to seal that stuff, because it's a triple whammy when you have duct leakage there. But in general, I was just trying to focus this on the system itself, not so much the whole house piece of it. But only one time have I been bit by not sealing ductwork, and that was a system where we combined. It was a ranch that had a system on both sides, and the duct really probably wasn't long enough running from one side to the other. And it had a crawl space which we encapsulated, which was nice. But I crawled in the crawl space. I'm like, it's warmer in the crawl space, and this is in the middle of the winter, than it is upstairs. Crap. I should have suggested getting this all sealed up. And it really it needed to be spray foamed for that one, because it needed not just sealing, it needed insulation. But in general, having a little bit of heating or cooling leaking, as long as it's in conditioned space, I'm not crazy worried about. And that's going to rankle some people, and happy to argue over it. But show me your numbers. You know, let's see some energy use numbers. Let's hear comfort from clients. If you can fit it in, great. But it's something that typically lands on the cutting room floor when we do budget.
Sure. Can the outsized air duct to the unit be sized to become a full economizer to reduce cooling in milder weather?
That's enough of a commercial question that I'm confused by it.
Okay.
I don't know.
And it looks like they
if you can clarify, please.
Yeah, let's see if they want to follow up. But I did have some questions about you know, the idea of the fresh air intake coming in, and I know there are systems out there that are shy of ERV, HRV that can supply and you can
Yeah.
control how much you want, but they're not the full-blown HRV, ERVs. What are your thoughts on those?
That'd be fine too, although you need to know if it fails.
Okay.
And the other curse is if that is running, but the air handler isn't running, you can be blowing so classic one. I've had two issues with ERVs causing comfort problems, and that was an ERV, not just a fresh air intake. And both of them were when it was like 5 degrees outside. So they're kicking out 45-degree air, 50-degree air. So it's noticeably cold. It's not freezing, but nobody wants to sit there. So if the air handler is not running continuously and you're pushing 50 or 100 CFM into the ductwork and then it's finding its way wherever it can, you're probably going to get a comfort complaint, which is why we just let's just run the air handler and get most of what we need. And this is retrofit world, and there are no rules in retrofit. So for new, you have to pay attention to code. The nice thing about retrofit is you can do what you want.
Right.
Was it Ron Swanson? I have a license. This is the cop after doing something he wasn't supposed to do. Like, this just says I do what I want.
Right. Right.
That's retrofit. You can do what you want, but you own it. So don't recommend something that's likely to fail.
Sure, sure. So this question, I think too, and I think it's more of a question of just kind of shouting to the sky, but maybe you can help us out with it. Why can't controls have an integral dew point calculator to set humidification and dehumidification in concert with fresh air delivery?
I wrote a whole article on my wish list of stuff that I'd like things to do, and almost all of it is control stuff. And I love it when they're like, well, dew point, that's kind of hard to figure out. Wait, isn't a smart thermostat a computer on the wall? This is algebra.
Right.
I can do it, but it's a pain. But this is an easy spreadsheet problem. Why are more people doing this? Yeah, that they should be controlled by dew point, and then I wouldn't get bit by my relative humidity set points.
Right. So is that the question? Is that a separate filter in the unit in addition to the typical filter at the wall in the living area?
Oh, that's a southerner right there.
Yeah.
So yeah, if you have central filters, typically they're going to be in a hallway. So this is a southern thing. Usually when you have attic HVAC, you wouldn't need a separate filter. In fact, that filter basically at the living space is really better than the central filter, because otherwise all the garbage is going to be in the ductwork before it hits that filter. And it would be better to filter it out before it even hits the ductwork in the first place. So no, it doesn't need to be a separate filter.
Thermostats. I mean, obviously, without getting into names and everything, what are you looking for? What do you like? What don't you like?
So if you're going to use modulating equipment, you're basically looking at top of the line manufacturer-based thermostats. Because if you put, say, sorry to mention it, but like a Nesta or an Ecobee or some other more simple thermostat, you can put that on a modulating piece of equipment, but then you take this equipment that can have 100 different speeds and now it has 2.
Right.
That's dumb. Don't do that. Put on a control that can control every capability that the equipment has. Just do it. And all of the controls suck in one way or another. They all have weaknesses. So
never good enough.
we use a lot of one particular brand, and anybody that saw the screenshots knows which brand we use. But they don't do data logging. So I can't watch to see what stage it's in and how much it's running in various things. So I need to put an energy monitor on so I can see the thing kick on and off. So nobody does everything that I want, which is why I wrote that wish list. If you Google the HVAC 2.0 wish list, and my hope is to, in time, get that in front of a bunch of manufacturers, because 80% of what we want is software. It's not, you need to make hardware changes. It's like, well, will somebody please get a programmer to go spend 2 weeks on it and get this done? Sure.
So we know that part of air quality or environmental quality, air quality is a big piece, but there's also sound, right? Sound can make or break our comfort. So the specific question here, and maybe you can add a little bit to it, but is airspeed a sound problem when you have to put a lot of heat in the house? And then I'm also just thinking of sort of dBA outputs of the systems you use. Do you think through that?
Decibel outputs.
Yeah.
Yes. So on high, a lot of systems are going to be at least a little bit noisy. I mean, in general, most existing homes really don't have much more than 3 tons of ductwork, so they can't handle more than, say, 1,200 CFM of flow. So that's part of why we try to aim everything to be a 3-ton system, so that it's not crazy noisy when it's running flat out. But the beautiful thing about these variable speed pieces of equipment is they're probably mostly going to be running at 25 or 40 or 50% of capacity, and they're just not that loud. The one that I showed with the ventilating dehumidifier on it, that was a hybrid system, and it's something I love doing. So the lady of the house is usually the one sensitive to sound, in my experience, and I love turning the system all the way up and then being like, so is that noisy? And getting the answer, is it on? Like, yeah, it's at 100%. That's all she got, Captain. But there are some that are noisy because I know they're light on ductwork. But in general, if you're doing variable speed equipment that dials down quite a bit, you're probably not going to hear it. There's been a number of systems that I've seriously had to go put an ear on to see if it's running.
I'm thinking this question, well, it's interesting. This question came in. Maybe you can just reiterate it. I think it's hard to imagine, where is the ventilator pushing the air in your HVAC2 reference. This person is mentioning that they don't have things like this in Europe, and they said thank you. But yeah, maybe you could, if that gives you some context to the question.
Yeah, that's a regional question. Oh shoot, is that Lars?
Yeah.
Yeah. He was asking me that question earlier. So this system design that I'm showing here is very US biased, because forced air systems are, I haven't seen the exact number, but say it's 90% of US homes have a forced air system along these lines. So this is what we have to work with. In Europe, when you have an older building, it's difficult to punch giant ducts everywhere, but you can punch the 1/2 inch, 1 inch holes to run pipes for hydronics through. Or you could do a small ductwork system maybe. And that would be the sort of thing, like I saw that one of the sponsors is CERV, CERV. And so that would at least, that has a heat pump with an ERV basically, so that the air coming out isn't super hot or super cold, because that is a problem. Like if it's 5 degrees outside, 10 degrees outside, the air coming out of that ERV system is going to be uncomfortable. It's going to be cold. Like it's going to be very cool. It won't necessarily be cold. It'll be 40 to 55 degrees, something like that. But in this system, we're just dumping it into the return right before the filter, so that outside air gets filtered. And if you're adding 30 CFM of air to a system on lows, usually running 300 CFM, you're only adding maybe %. So you're going to slightly drop the temperature, and then it's going to go through the system. So if the system's running, which it will be when it's very hot or very cold, you're never going to notice the outside air temperature difference. It should be eliminated. So
so you and I were talking about this before we went live, so I'm glad it came up. And according to this person, they believe it's complex to tie in HRVs and ERVs into existing systems. So they're saying, wouldn't it be better to use it as a low electricity ERV or HRV that's separate?
You could, but what's low when we're talking 15 or 20 watts with the air handler? You're going to spend $2,000 on one of those extra when you're talking, $250 in parts for doing this. You can, like, if you want to drive up the amount of airflow that you have, you can do that. But again, if it's humid outside, like, not everyone understands, like an ERV, yes, it will reduce the humidity of the air coming in to some degree, but it's still adding. So instead of bringing in 100% of the outdoor humidity, maybe it brings in 50%. But if you're bringing in a large volume of outdoor air, you have to dry that air, or else you're going to cause other problems. So very high flow rates in humid climates can be very challenging. So you're
saying when you make it a separate system, you're creating a humidity issue. potentially.
Yeah. Well, if you bring like an ERV is oftentimes going to run at like 100 CFM, and we're running more like 30.
Right.
So when you run the higher flow rates, all of the moisture that's in that air, you have to deal with.
Right. Right.
And one of our houses we could not control it.
Right.
And I was like, okay, I'm done. I'm not using these things anymore.
Right. Now they mentioned ease of install. I mean, I'd have to imagine that putting in a whole separate system in an existing home would be more work, duct system, than just integrating it. What are your thoughts there?
Well, I mean, you got 4 ducts instead of 1.
Right.
Because you've got 2 in and outs for an
Right.
ARV versus just 1 coming in. Now, one thing that wasn't brought up here that's worth mentioning, we like to pressurize houses just a little tiny bit. And it's funny, people are like, but you're pressurizing the house. Like, we'll measure how much. Like, we're lucky to even get the house to be neutral.
Right.
When you put up the blower door and you do your baseline test, most houses are running in the wintertime, negative 2, 3, 4 pascals. We are lucky to push that back to 0 with 30 CFM. Like, it's got to be really tight before we even push it to 0. But if you're pushing a little bit of air in, which it could potentially be problematic in winter, it's not super risky, but it could be. But in summer, if you are drying the air in the house and you're pushing that air very slightly out through the house, are you wetting or drying building materials? You're going to be drying them. So you're reducing moisture risk in the seasons when you have the highest moisture risk. So that's how we view that. We prefer pressurization. You can't use it for everything. Like we were talking about multifamily. Pressurization in multifamily is not a good idea, because if you have somebody cooking something that's really fragrant, the neighbor gets to smell it and they may not like it.
Right.
So, but in single family homes, a little tiny bit of pressurization is our preference.
So how do you take the HVAC 2.0, the BAD ASS HVAC concept, and how would you apply it real briefly to a new home? I mean, what changes would you make, if any?
Not a thing.
Yeah.
It looks just like this. The system in the basement of that 2018 house looks just like what you're seeing here. This works just fine. If you have to hit 62.2, you probably need to put in a 62.2 bath fan to make up for what this system won't do. Or you could do an ERV or something like that, or you do one of the pressurization fans like you were talking about, because there's a couple different models of those out now. There's a lot of ways to get there, but having monitored a whole bunch of houses, more than, I don't know how many people have monitored more houses than we have. I really don't. Like, there's a few, but like I bet it's on one hand that have watched more houses than we have, and a little bit of airflow seems to be fine. Surprised us. I didn't know, but it's like, so this is easy. Let's try this. If it's not enough, I let my clients know, so we can do this if you want to later. And we haven't had to do it. So
great. Well, Nate, we're pretty much at our time here. I don't really see any other specific questions, so I think we're going to wrap up. So Nate Adams, HVAC 2.0 co-founder, I really appreciate your time. And then before we wrap up, I guess the main question that I see from a few people is, how do they find and hire a BAD ASS HVAC contractor? I mean, that's when is this going to be possible?
So therein lies the big rub. That is why HVAC 2.0 is becoming a thing. So the 2.0 is basically a business model, but it's the easiest way to think of it is it's like applying the nursing model, because doctors don't really have a great process, frankly. Nurses have a really good process because they have to just repeatedly do the same thing. So we're applying a medical construct to houses. And so far we're seeing that our guys are seeing drastic increases in closing ratio and ticket sizes. So like, this is a better business model for HVAC contractors, and they're getting happier clients and they're not miserable themselves. So what we need to do is build that out so we have a nationwide network. It's pretty small right now. We're in alpha phase, but essentially you're gonna have to wait a year, or you could reach out to me and we do some remote consulting, and I can help you size it and specify it and then watch bids as they come in for you, if that's helpful.
So where do people contact you and find out more information?
That will be through NateTheHouseWhisperer.com.
Great, great. Well, Nate, super appreciate you coming on. I know I've been bugging you for some time, and so thanks for taking some time on a hopefully beautiful summer day for you as it is up here. We'll hopefully have you back to share some more cool stuff. But before we head out, everyone, just again, public service announcement. We want to beat this thing. We want to see you all in person, in real life someday. So masks, stay away when you can. And we hope to and improve. We need to improve our HVAC systems, right? We all need to work on this. So I hope we can get to work. I hope we can be together in person someday at a real event. And again, thank you all for your time. Stay safe out there. Bye-bye.
Bye all.